right, thank you. Thanks everyone for coming. It's great to see so many people here interested in machine learning and artificial intelligence like myself. So today I'm going to talk about making predictions using incomplete data, a specific type of incomplete data, in a case study of a battery life prediction. As Mette mentioned, my name is Jonas Mortin, and I work as a data scientist at Verisure Innovation here in Malmö. So first, before we start, I want to just get a feel for the crowd a little bit, see so from a scale 1 to 3, how would you say how knowledgeable you are in data analysis, mathematics, and machine learning AI? Where 1 is know little and 3 know much. How many would call themselves a 1? And a 2? And a 3? Okay, it's like an average of 1.7 or so. It's helping me out to kind of make the right level of explanation. So I'm thinking I want to do a continuous Q&A during this presentation. So feel free to ask me questions. And if I don't see your hand, just shout out. And but please, maybe the longer and bigger questions we'll take after. So just kind of the small stuff during the presentation. I'll try to leave as much time as possible for Q&A. Otherwise, we'll do it during pizza time. So the outline of this presentation is first I'm going to give you some context, a little background, then the actual problem, and of course the data and the approach that I chose to do to solve the problem, and then the results. So briefly about myself, which I heard now that Mette was supposed to do, but I gave myself a whole slide for this. So I've been working at Verisure for about 1.5 years, where I try to strengthen Verisure's system with machine learning and AI. We have a few pretty big things going on, and this is what I'm presenting today is one of them. I'm also helping to build our analytics cloud stack that we try to build at this moment. And I'm doing some classical business intelligence style reporting that I think most data scientists do. And also I mentor some workers and thesis students. Before this, I worked as a business intelligence consultant at Hypergene, where I primarily helped municipals to organize and analyze their data. I also worked as a research scientist at Stockholm University, where I looked at the surface energy balance over Arctic sea ice and its interaction with the atmosphere. Before that, I studied as a PhD student at the same department at Stockholm University, looked at Arctic seasonal changes using satellite-borne radar and state-of-the-art climate models. And before that, when I studied, I did a lot of different things like dishwasher, dessert chef, private teacher, DJ, courier, and a lot of different things. So on a personal note, I have 2 children and wife. I live in Bunkflostan, and I'm passionate about machine learning, AI, electronic music, and a lot of different other things. Here's the corporate presentation. We're number 1 in connected alarms in Europe. And we have over almost 3 million customers and a lot of employees in 14 different countries in Europe and in South America. So we have a large customer growth base year over year. It's accelerating. Verisure Innovation, which is kind of Verisure's research and development company, is located primarily here in Malmö. And we have more than 200 developers, engineers, designers, product owners, product managers, project managers, and everything. We sit here in Malmö. So Verisure, we have 12 main product types which communicate wirelessly, and most are developed in-house. And we also develop most of our software products and services in Northern Europe here in Malmö. So there's a lot of stuff going on in Malmö for Verisure's part. We collect about 50 million data points per day, primarily to ensure good health of installations and services. And we have about 9.6 million devices in the North European market. Out of these, about 8.1 million of these installed devices have replaceable non-rechargeable batteries, and they each have about 2.5 batteries each. So it mounts up to about 20 million batteries in our current portfolio that we need to replace at some point. Now these batteries need to be manufactured, shipped, stocked, stocked in multiple locations, there's a pretty big lead time from when we make the order of the batteries until we receive them. And nowadays, and I think that will increase over time, the problem, battery availability is not something that's guaranteed. There are a lot of people who want batteries these days, particularly the lithium ones that we're interested in as well. And these batteries are distributed in stock both regionally and also locally, down to in individual vehicles. And as you know, stocking is costly, but understocking is also costly, so you want to optimize it and make a perfect balance. The life of these batteries is an important quality indicator of our products. And the reason for that is that we control the batteries, we have non-typical form factors, and we test the products at the installation, meaning that the performance of the battery life is fairly straightforwardly connected to the performance of the products. So it's pretty useful for us, all in all, to know when the batteries will fail. So therefore, I was approached by representatives of the business with a few questions. 2 questions. How many devices of each type will fail due to batteries running out each month the coming 5 years? Also, when will X% of a product type have failed for the first time due to batteries running out? Now, if you can answer these questions, you can answer other questions that are truly helpful. For example, how do we monitor a healthy trajectory for product quality in terms of battery life, and then automatically track the deviations? How do we optimize battery stock to support field service optimally per country? How do we ensure battery availability and best prices 12, 24, 36 and more months ahead? Do we need to proactively hire and train technicians for upcoming service issues? How do we make sure our products work optimally, meaning better protection? If you can answer all of these or some of these questions, then that would help create a better product and service quality. And as you know, happy customers, everyone's happy and life's a party. That's kind of what we want, really. So this should be easy, shouldn't it? I mean, for each device, you can take 2 points of the battery state in percent, the one we have in all our devices, and then you extrapolate, right? So it's 100% now, when it's 0%, it's dead. It's pretty linear, right? You all know it's not linear. And not for us either. But if we would have known when each individual battery would fail, we could easily aggregate that and then answer all of those questions. But we use voltage to measure the remaining battery capacity. It's what you usually do when you have a battery-constrained device. And this is called the discharge curve. So if the discharge curve were linear, we could do this, or even near linear. But unfortunately, it's not. The discharge curve is primarily, its shape and form is constituted by its chemical composition and other factors, where temperature is a very big factor. Here you see to the top right, for the 2 most common types of batteries, lithium and alkaline. So lithium in green and alkaline in red. You see they have very different discharge curves. So this is the voltage you measure on the y-axis, and then time on the x-axis. And you see when it goes down a lot, there's no more voltage, meaning that it cannot function anymore, and it basically shuts down. This is a real measurement that we did on our batteries. So what you can see is that we use, like I mentioned earlier, we use primarily lithium batteries. And as you can see, this is pretty flat. Actually, I would say in real life, it's even more flat. This is a lab environment measurement. So it's at a given time for a given voltage we measure, we don't know what state we are in. So we can, if we measure, for example, 2,900 millivolts, we don't know where we are. We could be in the beginning, or we can be pretty close to the end. So we can't say anything about the state of charge of the devices. The only thing we actually know for certain is if a device has sent something called a low bat signal. A low bat signal is sent at a given threshold of voltage, which is basically the device sending a signal saying, hey, you need to replace my batteries, I'm going to die soon. So from the measurements of the capacity, we don't have enough information to make predictions about battery life. So we need another approach where we look at larger populations of devices. The battery life, the duration from birth to failure, is not stored directly. It usually isn't. So we have to estimate it. And the estimation we make is we take the time, the duration from installation, and until it sends the signal, the low-bat signal. And the low-bat signal is based on a pre-calibrated measurement, like I mentioned, which is calibrated so that device will continue to function for another 1 to 3 months. So this is a pretty good proxy for actually battery failure, as it's pretty short and it's relatively consistent. So we have a fairly good idea of what the real battery life. So when computing this for all devices that we have, we found out we have about 300,000 low-bat signals. Or actually 300,000 devices have sent low-bat signals out of 9.1 million devices historically. So 97% of the devices, they still haven't sent any low-bat signal. So if you want to include only the complete battery lives, we're only using 3% of the data. And remember, we don't know what's going on until it has sent the low-bat. So we can't tell anything basically on the state of charge. But shouldn't be a problem, right? Let's use what we have. That's kind of usually what we do, right, with data. So classical approach would be to start with the factors that affect battery life. For example, a camera takes images, and the more images it takes, the shorter is the battery life. So, and if you can quantify this plus other factors, then you can do some kind of prediction on battery life. The problem is that most of the data we have, the 3%, they're based on devices that are working, they're problematic. They died much earlier than expected. So the nominal battery life, the expected battery life for most of our products is 4 to 10 years. And as I mentioned earlier, our customer portfolio, it grows almost exponentially. And therefore, most of the devices that we have out in field, they're too young to have died, basically. And this is the main reason for the incomplete data. The thing is, since we're growing, it's an everlasting problem. It will always be a problem because there will always be new devices, and we will always have a problem with too little data to make good predictions. So using these 3% would be a real big mistake to assume that this sample represents a larger population, which is essentially what you do if you use that to quantify factors that affect battery life. And that will give you awful insights and misinformation. It's one of the ugliest words I know. And it should have been everyone who works with data. It's like, it's what you really do not want to do. You don't want to give misinformation to the business. So you need to include the active devices that are up functioning, just sitting there, and they contribute with some time to battery life, but they haven't yet sent the low-bat signal. But how can you do that? They're not real. They're not. You could always pretend that it's a complete battery life, but that would be a bad idea. So, but good for us. There are statistical methods that can include incomplete data. Survival analysis. It's a statistical branch used in engineering, sociology, medicine, and etc. It has many names, but it's an analysis of duration from event to event. And events can be anything, but classically, it's from birth to death. And it's an analysis in relative time. So we don't really care when the event started in calendar time, but it's only relative time that matters. An example is used a lot in medicine to compare different groups of those that get a specific treatment, those who do not get a treatment. And then you have the trial start, is the birth date or start date. And then if they die or get cured, is the event that you're looking for, the end event. And what's special about this is that it handles sensor data. And sensor data is a special type of incomplete data. Actually, so it happens, it's the type of incomplete data that we have. So let me show you what it means. Here are 5 different devices that we've mounted. Let's take the top one. It was mounted at time 0. We don't care when that was. And then at some point, 80 months later, it got a low bat signal. So we got the observed event is 1. We saw the actual final event. Here's another one who got a low bat signal after 40 months. Here's one who was mounted at time 0, and after 74 months, we don't have any more information about it. For example, the customer canceled and we took down the unit. But we still know that it sat there for 74 months, and that is some information about the battery life, but it's not complete information. And here is one that's most common for us. You mount it at time 0, and then after some time, it's today. So we don't know anymore. We know that it's still functioning, but we don't know anything else. And this particular example has been up for 85 months, and we have not observed the event. So for us, this constitutes about 97% of the data. So in survival analysis in practice, all you need, or at minimum, is these 2 columns, actually. And what you can get out is showing you 3 main components of survival analysis here. To the left, you have the probability density function, the PDF. It's basically, it's simply put the probability that the variant has a given complete lifetime. So in the discrete version, it will be a histogram of this list. There will be one who lasted 80 days, one 40 days, and so on. And then it creates this function. We also have something called the survival function, which is the probability of surviving beyond time t. So if this is time 0, you have a probability of 1 of surviving time 0. Right? But then as time passes, you will have lower and lower probability of surviving beyond that time. Right? So for example here, this is at x0, you have a probability of 50% of surviving. And this is the hazard rate. It's the risk or probability of dying in the next moment if you haven't died already at time t. And here you see that the hazard increases over time. Now these are different views of the same thing. They're mathematically coupled, and if you change one, you'll change the others as well. So there's more information here in the nerd box. So I have these on a few of my slides, and mostly I'm not addressing them, particularly not since we have a 1.7 as an average here today. But anyone who's interested could just soak it in. So these 3 are kind of the main components of survival analysis. I'm going to talk a little bit more about survival and hazard functions. So this is another example of a survival function. Usually you have incomplete data, otherwise you would most likely use another type of methodology. But that leads to that we need to estimate the survival function, because we don't know the distribution perfectly like we did in the last example. The most commonly employed estimate is called Kaplan-Meier. And it's a non-parametric estimate, so it makes no assumptions about distributions. And it's usually applied to separate populations that differ in some way that you want to compare. So in this case here, we're comparing, in this example, democratic against non-democratic regimes. And you interpret this as seeing that, okay, so it's more probable to survive if you're a non-democratic regent. Here you can see that after 10 years, there's a 40% probability that you will live past that. But in democratic regimes, the corresponding figure is about 8%, meaning we have elections, so you get replaced. That's kind of how you interpret this figure. And here's the hazard function, and this is the corresponding function. It shows you, in the same way you have to estimate it, it's a non-parametric estimate, and applied to separate populations. And this corresponds to the previous figure, where this is what is the probability of dying a given time, if you haven't died already. So in this case, you seem to max out at around 4 years for democratic regimes, meaning that that's probably when we have kind of a common election cycle. And also around 16 years For some reason, it's a bit lower at 8 years. If 4 years, I would interpret that as if you're being re-elected once, you tend to be re-elected more than once. That would be my interpretation of it. But you can see overall the hazard of dying a given day or being replaced is much lower for non-democratic regimes. Does this make any sense? I see some nods. Okay, I'm going to go with that. So here's a few examples from our products. So this is a survival function estimate of 5 major Verisure products. These are very similar, so it makes sense to compare them. So again, we can see, so from a quality perspective, this is really interesting. You can see how they diverge pretty early, and you see that they differ quite drastically in terms of performance for battery life. Yes? Yes. Very much. They're actually, there are 5 different cameras. So they're very similar. So it should actually be more similar than they are. But it's not a coincidence that this is an example. It's a good example. That's a good question. So going back to one of the main questions, when will n% of the population have failed from low bat? So this is the same figure, but it's zoomed out. So now it goes down to 0% probability. And we basically want to know what's going on out here. It's pretty tricky. But what do you usually do when you have something like that? You have a few lines and you want to extend the information. Well, you extend the information. You draw some line. You have a ruler or whatever you have. But basically what you do more formally is that you fit a function or a model to the data and extrapolate. You have to assume some kind of distribution. Otherwise you cannot do it. You need to fit it. In this case, you fit it to the PDF, the probability density function that I showed you first, kind of when they die. And then you get, from that you get the hazard rate and the survival functions through the mathematical extracts I showed you earlier. In survival analysis, you usually use exponential function, Weibull function, or log normal functions. So this is the same, but with a fitted function. So I chose Weibull functions. And what you can see is both the non-parametric estimate that I showed, this kind of wiggly line here, is the Kaplan-Meier estimate for 2 different products. And then there's a line which is a mathematical function that we think describes this non-parametric estimate pretty well. And if you, once you have that, you can extrapolate. You can say, well, this represents my distribution in some sense, so let's extrapolate. So this is the figure where it's extrapolated. I show these are the red lines are years basically. So you can see that we've zoomed out quite a lot, and it goes down to 0 again, 0 probability. And what we can see is that, well, for one product, it's about 80% chance of surviving longer than 10 years. And another one, it's about 60% chance of surviving more than 10 years. Now we know this is completely impossible. These are cameras. They cannot function for 10 years. It's not physically possible. So this doesn't make any sense. This cannot be right. And the reason for that, there are 3 reasons primarily because we can't answer the question in this way. One is that we don't capture the normal failures due to old batteries. Like I mentioned earlier, we have a subpopulation that die early. They're malfunctioning units, most of them. So this is what we use to fit the data to. And battery life cannot be described by one single function. And also we have too much censoring our data. 97% is very much. When I started reading about this and I asked the internet in different forums, when there's extremely much censored data, how much is it? And most of them said, well, if you're over 70%, it's a really difficult problem. And we're at 97%. So we have a lot of censored data. So after doing some research, there's only one model that makes sense when you work with batteries. And it's the mixed Weibull function, or the bathtub curve. Now this function is really well known within quality work and reliability analysis, but yeah, and I'm gonna explain it first. So the bathtub curve is called the bathtub curve due to its shape, and this consists of 3 different functions that are superpositioned. And this is the hazard we're talking about, the probability of dying the next second or day if you haven't died already. So first you have the early failures, the infant mortality. Those kind of måndagsexemplar, we would call them in Swedish, kind of the ones that are just really poorly working. And then you have some constant failures that they can die for any reason. And then you have the wear-out failures in yellow. They die of old age, basically. If you superposition all these 3, you get the observed, you get the bathtub curve. I realized why this I couldn't find any software that could implement this, and it turned out because it's really tricky to do it. I'm going to show you an example here. This is 2 different devices, or products. It's the same I showed you earlier, and this is the hazard function. So it's a probability of when they die, basically. What we see is that it increases instead of decreases, which I think is due to, since we do a quality check when we install the devices, it's basically just, it takes some time to diminish the battery, to deplete the battery. And then you have some kind of constant phase, and then at some point it really takes off. And actually, this is an old figure. When I mean take off, it kind of goes up here. It just takes off completely. That's how batteries work. When they start to die off, they really die off. The probability for every day really increases drastically. So again, we need to extrapolate. We want to know what's going on out here. We don't know that. So I'm going to try to very briefly describe this methodology that I used in order to do so. And I'd be happy to talk in larger depth after, if anyone's interested. But basically, we have these 3 different segments that corresponds to these different reasons of dying, basically. I cannot do some kind of inverse modeling because they're superpositioned, but I'm just saying that, okay, they correspond to these 3 different segments, and that's it. So this one I fitted to data, a variable function. And here's also a variable function to the second segment. And then the timing between these, I do basically a brute force search. I just test all different combinations, and then I'll see which is the best fit. So again, I'm doing this on top of the estimates of the hazard that we got, based on actual deaths. So we have a lot of data here and here, but this is where we don't have much data, and that's the whole problem. And this is where, because this one is the one that really takes off, this is the most important one to have data in. But here I can do a few assumptions. For example, I can see that I fit data where I have data for some old types of products, and then I can apply the same to newer products. Until we don't know how, for example, the Smoke 2, which is it's pretty old, but it's kind of up here, the oldest ones. We don't know exactly when that starts to die off. Until then, we can use the information from Smoke 1, which is really old, and it's over here. So we can reuse information in a good way and make solid assumptions, and then we can kind of lay a puzzle where we always get the best available information. And then, of course, we automate all this, so we only have to look at it maybe twice a year or something, and then it's really nice when it's low maintenance. Okay, I think that I'm gonna stop there with the explanation of this. Like I said, I can talk more about it later if someone's really interested. Okay, let's look at some examples. So here we have a real hazard function based on historical information. This is all we know about this particular product. And it's the one I showed you earlier as well. So first, they don't die off basically the first year, and this is the first segment. Then the second segment in here, and you see the fitted function here. It's fairly constant, and then at some breaking point here, it just takes off. Now I've decided that that is right here because it makes sense. There's some manual work to it at first, but this actually fits really well for other similar products. Yes.
How do you fit segment 1 if you believe that it's misrepresented if the quality checks?
I don't think it's misrepresentative. How do you mean?
You mentioned that the data looked a bit different from the label.
Oh yeah, from the theoretical bathtub. Yeah, I'm letting it. I think it's not due to its. I think it's basically because batteries function a little bit different than other types of units, and because it takes some time to drain, even though the device is problematic. And also, since we do tests when we put them up, the worst one they're not put up at customers, and therefore our available function for the first segment looks a little bit different than for maybe other typical products than you would apply to. And this is actually both the increasing and this pretty constant one in the beginning. I see that in almost all our products. So it seems to be representative. I would say that this is a representative example together with the other one that I showed you that kind of increased a little bit more. And it's this one. So these two actually represent the kind of two main types that I can see. And here we see an increasing first segment, pretty constant the second, and after that we don't have more data. We don't know what's going on, so I'm going to apply my. I have older versions of this product that we have more data, and I know that okay, this makes a lot of sense. So it's like drawing in the air, but it's based on really solid assumptions. And I've of course talked to experts within the company as well that says that okay, this makes sense. So after all our functions have been fitted, we have both the non-parametric estimate, which is kind of based on historical events, what actually happened, and we have the parametric function, which is us saying, well, I should probably use this ruler to extend the line. So what I do now, this is I kind of assemble the hazards. So first I use as much as historical information as we have, and then at some point we don't know anymore, so I have to extrapolate based on the logic that I just talked about. So how far do we need to extrapolate? We can extrapolate to infinity. For different reasons that I'm going to come back to, we'll extrapolate so that the area under this, the integral of this is 1. Otherwise, we'll be doing upscaling and downscaling of populations. I'll show you why in the next slide, I think. So this is kind of given the available data that we have today. This is the best information we have on basically the probability of when a device is going to die. A lot of work. Yeah, we want to know as early as possible. Basically, what the business wants to know is they want kind of table of the coming 5 or maybe even 10 years. I've heard how many is going to die every month. How many batteries do we need in stock every month? Because they need to budget for it. They need to negotiate with battery suppliers several years ahead. I can't. Well, yes. That is basically what we're interested in. It's kind of our definition of end of battery life. Yeah, well, it's only our best guess right now. And the further you look ahead, the more insecure you'll be. We probably know how many is going to be tomorrow by looking at the last 3 months. We know the next month is pretty linear relationship for a short time ahead. I think, could we discuss that when we've come a little later? I think it'll be a better discussion then. So what are we going to do with this? That's basically what you're asking a little bit. Like, what's the use of this thing? And that's right, that's a good question. Well, in order to get something out of this, because sure, this is good for quality work and so on, but we want to know, like I said, when will they die? So this is the probability of when they're going to die, basically. Now, if you convolve this, basically a multiplication of distributions, if you convolve it with the distribution on when they're installed, then you will get out this thing that we're looking for, which is the battery prediction in calendar time. So what you see here is the plot in calendar time. This is number of devices per day. And the blue is how many we installed. And the red one is the prediction. And the green one is the actual outcome. And you see that it ends mid 2018 because that's where we are now. So this is what you get out, basically. Now, you can aggregate this in time if you want to know per month, or if you want to know for several products, it's easy to aggregate. And you can also slice and dice this installed devices if you want to know for a specific country or a specific type of customer, like someone's last name is Svensson. You can just you can slice that and before the convolution, and you get the battery prediction for that population. So this comes from a dynamic self-service report. So it's pretty convenient for the end users, basically. Sounds like I'm trying to do a commercial for this particular for this report, but I'm just showing that it's pretty dynamic and useful. It's not super specific. You can kind of select what you want to see, and that's the whole point. I want to build it as general as possible. Another way of showing that is this, and I don't know why, but they're always very interested in seeing tables. I don't see the point. You don't have any overview at all. This is the same information. You can see that's clear as this one, isn't it, right? I don't know why, but never mind. So you can show it like this, and you can see, okay, so number of batteries of what type per month, and that's what they want. Yep.
Just out of curiosity, how much is there any change in the data you get in from battery vendor to battery vendor, or from battery batch to battery batch, or are you able just to neglect?
In this case, I would say it's a fair assumption to neglect it because it's been tested on that particular device, and this discharge curves, they look different from different vendors, and we use different vendors for different products so that they're kind of optimized. So in this case, actually, it's pretty nice. And since they're non-standard form factors, like not these AA, AAA batteries, people don't replace them themselves in the same extent. But if they do, we don't know. I mean, you know, the typical remote control problem, you only have one battery left and you replace only that and everything seems to work fine. But you don't want to do that for kind of core security units. And we wouldn't know that they did that. Yeah. It's a good question. I think it's fair to assume that it's fairly constant over these short time periods that we negotiate for different I would say that it's that we can discard it for this analysis. I think it would be an interesting problem looking at it. But I don't think it matters during these relatively short time periods. Yep.
Change that question around and say, how do product cycles affect the same methods? Newer products
Yep.
are more optimized
Yep.
than older products.
Yes. In some sense they are, and some they're not. Some are performing better and some worse. We have a lot of, I mean, they usually what you do is that they become, for example, a camera has higher resolution, it's in color, it has more features basically, which means that, but it also increases battery. you kind of get the same battery life. It's a reasonable assumption. It's the same with basically computers, right? They become smaller and smaller, but they have roughly the same battery life. Yeah. Yeah. To be able to say something about the different batches of battery or different vendors and so on. Oh yeah, yeah. I see your point. I think the problem is that we don't have enough. We don't have enough low bats. Basically, we still only have 3% of the devices that are sent to low bat. So a very, very small amount of data to be able to do such. To be able to tell anything about the product from that point of view. So it's we have too little information basically. At some point we'll be able to do it, but on really old devices. And then they basically all died. And then we have this new thing which haven't been up for long. And we still have the same information problem basically. So you'll be kind of just pushing the problem ahead all the time. Did I answer your question? All right, let's talk more later. Right. So let's go back to these initial questions that kind of is what we want to go for. So how many devices will fail from battery failure each month coming 5 years? Answer that one, right? When will X% of a product have failed from batteries the first time? So this one answers the first question or some derivative of it. And this is actually, it's just the same information, but it's aggregated over time. And then it's normalized with the total population. What you get is you can say, okay, so at roughly 2023, half of them will have died. And this doesn't make much sense in itself, but if you compare different products, it will make sense. Yep. Yes. No, I have not been asked to do that. It just scares people off. But you're right. Yeah, it's not here. And it's something that I'm working on right now to produce. So I will have one soon. It's important to have that. Good question. Yeah, so everyone's happy, right? So yeah, to your question, the model validation. No formal validation on the model output yet, unfortunately. Even though it's best practice, I apologize for this. But the reason is that there's not enough data, I think, to validate properly in a relevant fashion right now. Basically, we need to move up that third segment. Otherwise, the model will look really good. It will look super good for these first ones because they don't matter very much. It's the last one because it's so different than the others and it really takes off that I have to wait a little longer, and I expect it to be just in a few months. We basically have more that have died off on the older units. And I'm currently implementing the confidence intervals, like you always should do. So a few comments on this, just caveats and pitfalls and so on. The product version, which I've been kind of talking about the product, and I haven't talked much about it because it's kind of unnecessary detail, but the version of each product, it's the most important factor for battery life I've found. I found it in a pretty extensive analysis because it's kind of the whole analysis builds on it. But you could really slice on some other dimension that is the most important factor. If you don't have one or two factors that are much more important than the others, this is not a good way to do it. Yeah, version is the hardware and software combination. So if we change software or we change either or, it will change version. So I've analyzed these separately. And this works best for larger population, not very well for individual nodes. This kind of goes back to your question. Well, technically, we can project these hazards that we get from the full population down to one individual and say, well, if they all behave like this is what this particular one should behave like, but that's not right. They only behave like that in a larger population. So it works best for larger populations. Also, the output wouldn't make much sense. I mean, it's a 0.05% of this device will die the day after tomorrow. It doesn't make any sense, but if you have 1 million, it makes sense that 5 or 50 or whatever it is will die the day after tomorrow. And you can extend this analysis to other events, but you will require other functions than the mixed variable. Also, this is my final slide. Just a few words on the survival analysis framework. There are so many different types of methods that can incorporate sensor data, which is basically what survival analysis is. This is one taxonomy I found in Wang et al. 2017. It's there are a lot of different. I think it's a bit overly detailed, but sure, there are. We kind of did this green and blue boxes in this particular analysis, and they don't say that that's machine learning at all, and they have all these survival trees and Bayesian methods and random survival forests and all different types of methodologies. I haven't attempted to do so to go for any of these, even though that would be very interesting because there's not much information on them and they're pretty new, and I'm not even sure how robust the code is. I think it's a lot of active research on this, and I think it works best in research for now, at least the little I saw. Yes, but I would be very interested to look at more at the Bayesian statistical framework for doing this as a prior posterior functions. I think it works really well. We have a prior will be kind of for the last. I'm just going to pretend that you all know what I'm talking about. So if you have for the last product, you have the prior. You say, well, we assume that not knowing anything else, it will behave like the last one, and then you update that with when you get new data, and you get what's called a posterior function. That would be very interesting, but I didn't, for different reason, I didn't look at that at the time. So I would say that this approach that I took was just one out of many. But when you're in this situation, when you have incomplete data, you have to have the methodology, whichever you choose, needs to be able to include sensor data. And that's kind of what you're looking at here. You have this to choose from, plus like 1,000 more with weird long names. But this is what you have. Otherwise, you will create a lot of confusion in the business. Yeah.
So when it comes to the machine learning part of the data applications and analysis, I haven't really understood how you integrate that with the way you analyze, and if there's any key structure where it develops further the analysis other methods.
The machine learning is primarily here. See if I can find this one that I kind of skipped over. There are a lot of details in this. I tried to make it not too detailed technically, but this is basically the machine learning part of it. We fit functions, which is also the machine learning. I know it's usually you want it to be deep neural nets and really fancy, but this is kind of the old school, unsexy machine learning, right? So we fit variable functions and kind of do brute force searches and so on. So you still have this kind of more modern approach to data that you didn't do before, but it's still classical methods. Yeah. It's manual. It's just I decided what range it is and just test them all out, and then I use a sum of squared residuals to see which fit is the best. It was the best. It was the best goodness of fit metric I could find. I tested others as well, like the Bayesian and Akaike information criterion, but they didn't perform as well.
Okay, but
Um, this is pretty lightweight. This is a Python script that runs in a few hours for 10 million devices. So, and it doesn't need to update very often either. I mean, we don't get much of this death data. So every week is fine. So it's this little thing that just spins on a server once a week for a few hours. And then you can use that in dynamical reports with the installation basis, which updates every day, which is really easy to get hold of. So it's pretty lightweight. So it would be nice to roll it out and Hadoop clusters, but it wouldn't make any sense at all. It's really small. Yeah. All right, that's it. Thank you.